Welcome back to Codex. Our speaker today is Sho Suda, who is an associate professor in the Department of Mathematics at the National Defense Academy of Japan. Professor Suda received his PhD in mathematics from,
Tohoku.
Thank you, Tohoku University, under the direction of Akihiro Manimosa.
Yep.
Sho is an expert in algebraic combinatorics, in particular association schemes and spherical designs. Today, he will tell us about equiangular tight frames. Take it away, Sho.
Yep. Thank you for introduction. So, and also I'd like to thank the organizers for giving me this next chance. I'd like to talk about recent topics on equiangular tight frames. And in this talk, I would like to deal with two topics on ETFs. So the first part is about the construction of the equiangular tight frames over real number field or complex number field or the quaternion numbers. This talk is, this part is based on joint work with Hadi Kharaghani and Thomas Pender from University of Lethbridge. And the second half topic is about conjecture. This conjecture was posed very recently by three mathematicians, Shu and Yu. That conjecture is about existence between two real equiangular tight frames. And this part is joint work with two of the authors, the Zili Shu and Wei-Hsuan Yu. Okay, so the first half part, I like to consider the equiangular tight frame of quaternions. So let H be the set of quaternions. In this talk, I use this symbol asterisk. This is just conjugate of the quaternions. The definition for equiangular tight frames for quaternion case is exactly same as the other number field, complex real number field or complex number field. That is the set of unit vectors in HD, the dimension D, quaternion numbers, vector space, and we consider this matrix V, and where each vectors is the column vectors, and the ith column is the ith vector of the set, and this set is said to be equiangular tight frames if the following two conditions hold. V times V star is a multiple of identity matrix. In this talk, I denote the identity matrix, and the second condition is about the equiangular conditions for any distinct indices K and L. The inner product, absolute value of inner product, the K's vector and the L's vector is constant, say C. And from these definition, we can determine this value C, like this. This equiangular tight frames of quaternions have been recently studied by Waldron in the paper tight frames of quaternions and equiangular lines. Of course, maybe 30 years ago, already Hogarth considered the equiangular lines of a quaternion case, and Waldron developed its theory over the quaternion case. Our contribution to this topics is about to construct equiangular tight frames for orthogonal designs. Okay, so in order to show our result, I need to define orthogonal designs. So, so Hadamard matrices is a very famous object in combinatorics. Hadamard matrix H is an n times n square matrix whose entries are 1 or -1, such that the H times H transpose is equal to n times identity matrix. This means any two distinct rows are orthogonal in the matrix H, and this is maybe the simplest example of Hadamard matrix of order 4. This is a ±1 matrix, and we can easily check. any two distinct rows as orthogonal. And as a generalization of Hadamard matrix, so I like to define the orthogonal design, which is denoted by X, and of order n and type S1 to the SL. It is an n times n matrix whose entries are the variables from plus minus x1 to the plus minus xl, such that x times x transpose is a scalar multiple of identity matrix. But this this is a quadratic polynomial s1 times x1 square plus up to sl times xl square. So this is a typical example of orthogonal design of order 4 and of type 1, 1, 1, 1. So order means the size of this square matrix, and type means each row. In each row, each variable xi appears exactly one time. So in the first row, x1, x6, 3, x4. So this corresponds to the type 1, 1, 1, 1. And just same as the Hadamard matrix case, we can directly check any two distinct rows are orthogonal in this matrix X. So this is truly generalization of Hadamard matrix in the sense of that if we substitute plus minus 1 into each variable xi, then it is the Hadamard matrix of the same order. As also, this object orthogonal design can be used to produce the larger size Hadamard matrix. So this is very convenient object in the combinatorial matrix theory. This concept is introduced in our paper with Hadi Kharaghani, 2019, appeared in Discrete Mathematics, and we introduced some concept for Hadamard matrix. Balancedly splittable. This means if we suitably permute the rows of Hadamard matrix so that H contains some submatrix H1, such that H1 satisfies these conditions, which is the H1 transpose times H1 has just two distinct off-diagonal entries. So if we write this condition as the matrix equation, so we arrive at this equation, H1 transpose times H1 is equal to a linear combination of identity matrix plus some symmetric 0, 1 matrix that is the adjacency matrix of some graphs plus some multiple of j minus a minus I. Here j means the all ones matrix. So I think the most interesting case is this scalar b is equal to the negation of a. In that case, the right-hand side of this matrix equation can be written as the di plus a times some matrix S, where we set this matrix S. So in this case, we have the following proportion for balancedly splittable Hadamard matrix, and if it is the case, namely B is equal to negative A, then this matrix 1 over square root of D times H1 forms an equiangular title frame. This means that each the set of columns of this matrix form equiangular title frames. I think this concept, this situation is exactly the same as the Hadamard title frame that already studied by the organizers Felix, Jasper, Mix, and Peterson. And I like to point out that in our paper, we consider not only B is being minus A, but also the other case. And in the other case, we have we can connect this concept to another nice combinatorial object, such as strongly regular graph or symmetric designs or mutually unbiased basis. And we also gave some construction of this kind of Hadamard matrices, and also construct some association scheme from this object. But some works, I think, overlapped with the work in Hadamard title frames. Okay, so in the first part of this talk, I'd like to generalize this concept or this result to orthogonal designs over these three cases: real number field, complex number field, and quaternion numbers. Okay, so in order to get the result, we need a definition of quaternion Hadamard matrix and the quaternion orthogonal designs. So this is just we change the base field R to the quaternion numbers, but this is the definition of quaternion Hadamard matrix. This is again square matrix, but the entries is plus minus 1, plus minus I, and plus minus j, and plus minus k, such that this matrix equation holds h times h star is equal to ni, where this h star is the conjugate transpose of h, where conjugate means this defines like this. And the quaternion orthogonal design is the square matrix X of order n with entries from this set plus minus epsilon L times XL or plus minus epsilon L times XL star, where index L runs over from 1 to U, where U is the number of the complex variables, and the epsilon L is the coefficient of the variable, and this is in the set. Epsilon L takes 1 I, j, or k, and the most important thing is this matrix equation. X times X star is the multiple of identity matrix, and here the scalar was a polynomial SL times XL times XL asterisk XL star. In this case, we denote X as a quaternion orthogonal design, so QOD n and S1, S2 up to SU. Okay, so this n is the order, and SI is the type of the orthogonal designs. So if epsilon L takes just two values, 1 or I, then such OD is said to be complex orthogonal designs, and I denote it by a COD. And this is the easiest example of the QOD, quaternion orthogonal design of order 2 and type 1, 1. This is the example A bar, BI, B bar, J, AK, where A and B are variables. A is equal to, we may regard A as x1 and we may regard B as x2. And also over bar means in this talk negation of such symbol. This means A bar is equal to minus A, B bar is equal to minus B. And
Sho?
yeah.
There's a question in the chat, which is the complex I the same as the quaternion I?
Yeah.
Thank you.
So exactly speaking, we need to we just restrict the base fields this case. So okay, so what I want to emphasize is bar is not a conjugate, but just a negation of symbol. Okay, so this is the definition of the property of balancedly splittable for orthogonal designs. Let X be a orthogonal designs, and it is said to be a balancedly splittable if X contains some submatrix of size D times N. And the condition is X1 asterisk times X1 can be written as the off-diagonal entries of this product is the of this set. Okay, so sorry, this is the definition of the Hadamard matrix case, just taking the two values on off-diagonal entries. In orthogonal designs case, the off-diagonal entries can be written as the just a quadratic monomials. But this definition is complicated, so I'd like to show you some example in the next few slides. But this concept is considered in our paper, Kharaghani and Thomas Pender and me, the balancedly splittable orthogonal designs and equiangular tight frames.
Sho? I think we lost you. I can still see you, but I can't hear you. Is that true for everybody? Cool.
Son, where are you?
Yeah.
I'm not sure.
The sound kind of cut out as if maybe a cord got loose or something.
Yeah.
Yeah, we can't hear you right now.
Maybe unplug your cord and plug it back in.
Okay, is that
There we
okay?
go.
Not-
Yep.
We can hear you now. Perfect.
Yep.
Hey,
Sorry about that. Okay, so this is an example of balancedly splittable complex orthogonal designs of order 16 and type 8. In this example, also we use these two symbols A and B, and they are variables, and again X bar denotes the negation of X, and we can check this matrix is a complex orthogonal designs by maybe not hand, just mathematical. This is the also complex orthogonal designs, two variables. And if we consider the upper half submatrix here, 6 times 16 submatrix here, I denote it as by X1, and this matrix is has a property of balancedly splittable. This means if we consider the product of this one, X1 times X1 can be written as this 6 times 16 base matrix, and each of diagonal entries are the quadratic in the variable A and B, and diagonal entries are C or D, where C is equal to the A times A star plus 2 times B star, and where D is 2 times A star plus B times B star. Okay, so A and B are variable, complex variables, so we can substitute any values of complex numbers. So if, in particular, if we substitute the complex number with modulus 1 into these two variables A and B, we can easily check the diagonal entries are always constant, just 3. So this means the columns of this matrix X1, which is multiplied by 1 over square root of 6, form a complex equiangular tight frames. Because this matrix X is an orthogonal design. So X1 is any two distinct rows of X1 are already orthogonals, and this matrix shows that any two distinct columns, their product is the constant if we substitute these values, the complex numbers with modulus 1 into two complex variable A and B. So this means this matrix form a complex equiangular title frames with parameters and 16. Then the most interesting point for me is this complex equiangular title frames. The entries are parameterized by variables, so we can we have a non-rigid equiangular title frames from complex orthogonal design. So second example is the quaternion case. This is also quaternion orthogonal designs that we have two variables A and B, and the coefficient is 1 or I or J or K. And also again, there should be something wrong. Maybe this horizontal line should be like here. I would like to consider the 6 times 16 some matrix of this quaternion orthogonal design. But the X1 asterisk X1 has similar structure as before complex orthogonal design case. So almost same things happens. The off-diagonal entries are quadratic, and diagonal entries are C or D. Again, these variables are the same as before. And also, if we substitute the complex numbers with modulus 1 into each variables, then the diagonal entries are exactly the same. These are 3, and this means 1 over square root 6 times X1 form a quaternion equiangular title frames. Also, the most interesting point for me is its entries can be parameterized by variables. So we have, in this case, the non-rigid equiangular title frame. Okay, so in the first part, the construction is like this. So if we are given a orthogonal design of type of order n, so we can construct some larger orthogonal design of order 4 times n square from the old one, xn. This. Okay, so the technique is just as a matrix equation. The proof for checking this theorem is maybe just a linear algebra, but the construction is like this. So we consider this type of 3 times 3 block matrices, and we put some matrices defined like this. So assume Xn has the rows R0 to the Rn-1, and also assume we have a quaternion Hadamard matrix of order n with rows H0 to the Hn-1. We consider this the row vectors Ri hat on the Hi hat, just we doubling Ri or just doubling Hi, and also consider some square matrix Ci Hi asterisk times Ri, where each Ri is the row vectors, and the Hi asterisk is the conjugate transpose of Hi, and Hi is again the row vector. So this is the column vector times row vector. So this is the square matrix. And using this matrix, so we consider some matrices A and B. This is a block circulant matrices whose first row block consists of C0, C1 up to Cn-1, and Cn-1 up to C1. And B is just a negation of these parts from A. And E and F are the some block column matrix or block row matrix, and each submatrix, subblock, EI or FI can defined like this. This is something similar to the definition of CI, but the the indices are not same. Here H0 star and Ri hat, so I is not equal to 0. So and G is H0 star hat and R0 hat. So anyway, so if we put these matrices like this, GF minus F, EAB and minus EBA, so we can directly check this matrix X4N square is the orthogonal designs. So if you are interested in the proof of this construction, please see this paper, balanced splittable orthogonal designs appeared in design codes and cryptography. Also, this orthogonal design has very nice property because if we consider this submatrix, second row block submatrix EAB, this forms essentially the equiangular title frames. I just normalize some values. That is the 1 over square root 2n square minus n times this matrix H, the second row blocks EAB, forms a quaternion equiangular title frames. So also this proof is straightforward, just calculating the H asterisk times H. And in this theorem, we need some the smaller size orthogonal designs, and using that, we have a larger size of orthogonal designs in the recursive construction. So I didn't mention about the existence of QOD, but the exact construction are already given by several authors. For example, if you are interested in the explicit construction for orthogonal designs of quaternions, please see the book by Jennifer Severi, Orthogonal Designs. As also, in this paper, in our paper, we consider another submatrix. For example, this column row blocks FAB. So the transpose of this matrix also forms another type of equiangular title frames, but they are rigid. Such the entries the variables have variables, but the ground matrix is fixed. So if we consider the horizontal vertical blocks, then we have a parameterized ETF, but the ground matrix is always same. So I think this the submatrix EAB is interesting in. Okay, so this is the first part of this talk. Okay, so next I would like to consider another topic about existence of the real equiangular title frames. So the very recent paper, Zili, Sho, and Wei-Hsuan appeared in Electronic Journal of Combinatorics the title of the paper is Bounds on Antipodal Spherical Designs with Few Angles. They propose the following conjectures. The existence of the following are equivalent. The first object is a real equiangular tight frames with parameter d times d plus 1 over 2. And the second object is that with the parameter d minus 1 times d minus 1 times d plus 1 over 3. The main result in the second part is to show an implication from 1 to 2, but we need some extra assumption. So I like to show you how to prove this implication and what is the assumption, what the assumption is. So in this case, we use the concept of spherical designs. This is the finite non-empty set in the unit sphere, and this is said to be a spherical T design. If this equation holds, this means the average of F over the finite set X is equal to the average of F over the unit sphere, where F is any polynomial of total degree is at most T, and there is a natural lower bound for the size of spherical T designs. If T is even, the size of X is at least this value, and if T is odd, and the size of X is at least this value. But these values are not important in this talk, but there are natural bounds, and if equality holds, then the spherical design X is said to be a tight. And the tight case is very interesting, and the classification has already been done, except for 4, 5, and 7. The determining the existence of for the case 4, 5, and 7 are very interesting of a problem in the theory of spherical designs. In the second half part, I like to construct the some equiangular tight frames from the another dimension equiangular tight frames. So to do so, we rephrase the equiangular tight frames in terms of the spherical code. In the slide, we give some equivalence between equiangular tight frame, real equiangular tight frames, and some spherical designs satisfying some conditions. Okay, so let X be a finite set in the unit sphere with size n. And I didn't mention, but the X is the equiangular tight frame. If and equiangular, then the set of inner product between two vectors, two distinct vectors in finite set X forms this set. This is the inner product between two distinct vectors. And so this means just equiangular conditions, but using the result by the result Gotthard-Seidels in spherical designs as codes. So if the X achieves a Welch bound, this union X and minus X forms the spherical 3 designs. So equiangular tight frames is just almost same as the spherical 3 designs, and it is antipodal. And its inner product set consists of just 3 values, plus minus C or minus 1. So in equiangular tight frames, we have just equiangular conditions and frame operators condition V times V star is a scalar multiple of identity matrix. But if we consider the union of these two sets, we have a antipodal spherical 3 designs with 3 distance set case. So anyway, we have a following observation. For final set X, the following conditions are equivalent. So the first one is X is a real equiangular tight frames with some parameters. And the second condition is X, the union of X and minus X forms an antipodal spherical 3 designs such that X and minus X has no points, and the inner product set of X, the union of X and minus X are just these 3 values. So using this observation, so I like to construct X satisfying these conditions, Okay, so this is the conjecture by Shu and Yu, and they conjecture these ETFs. The existence of these equiangular tight frames are equivalent. And first, I like to mention this ETF in first case is nothing but a tight spherical 5 designs. And the second ETF lies on the S to the D-1. The dimension is 1 less than the first case. So the question for this conjecture is about, so how can we obtain an equiangular tight frame in S to the D-2 from equiangular tight frame corresponding to the tight spherical 5 design? So the partial answer for this question is it's possible when we can cut the equiangular tight frame in the first case by 3 parallel hyperplanes. I will show you what happens in the easiest case in the next slide, but this is the partial answer under the situation, and this condition is equivalent to the fact. So there is some vector alpha such that the inner product set between the vector alpha and this set, the union of X and the negative X, that consists of inner product alpha and X. This set contains exactly 3 values, 0 and plus minus A for some positive real number A. Okay, so this is the smallest the situation of the simplest case in S1. And in S1, so tight spherical design is just a regular T+1 gon. And in this case, we have a regular hexagon here, 6 points on the unit sphere on the plane. So these 6 points lies on the 3 parallel lines, this line and this line and this line, trivially, right? And these 3 lines, the normal vector is like this vector is alpha. So our question was for tight spherical 5 designs, does there exist a vector alpha such that the inner product between the vector alpha and the set of X, the union minus X, consists of just 3 values. So in this case, these 6 vertices form the tight spherical 5 designs, and if we take a vertex alpha like this, then the inner product between alpha and these 2 points are the same, and the inner product between alpha and these 2 points are the same, and also in this case. So in this case, this alpha satisfies these conditions. The claim is if we have a larger dimension equiangular tight frames, and if I could find such vector alpha and consider the vertices on the some hyperplanes forms an equiangular title frame in one less dimension unit sphere. So next question is how can we find such vector alpha? And in that case, the answer is if we consider some lattice generated by tight Spherical 5 designs, and if its lattice satisfies some property, that we can find such vector alpha. And this red colored word, some property, I would like to explain it in the next few slides. And this concept, this property was already studied by the paper. The authors are the Bannai, Munemasa, and Nebe. Okay, so I'd like to move on to some lattice generated by the Spherical 5 designs. Okay, so this is a setting. Let X be an equiangular tight frames with some parameters. And this parameters case, X and the union of X and minus X from the tight Spherical 5 design. Okay, so and the inner product set is something like this, plus minus 1 over scalar to d plus 2 and minus 1. So if tight Spherical 5 design exists, then d plus 2 must be some square of odd integer. So this means this inner product must be rational. So we can show this claim by some number theoretical technique. Anyway, so I use this symbol n from now, and we consider the D, the set D. This is a scalar multiple of tight Spherical 5 designs. The scalar can be defined by this value n. Then the inner product set of D forms just integers. In original tight Spherical designs, this is a rational numbers, but not an integer. But if we multiply this set, then the inner product forms just integers. So now we consider the lattice lambda generated by D, this set D, and this lattice is so-called integral. This means the inner product always the integers for any vectors in the lattice, because this is true because this A of D consists of integers. So this lattice is just a integer linear combination. So we have these conditions, and also we consider dual lattice L denoted L asterisk. This is defined by these conditions. Its set consists of vectors. Such vector X satisfies these conditions. The inner product X and Y is integers for any vector Y belongs to L. And the lattice L is the integral. So the original last must be in the dual lattice L asterisk. Okay, so now I like to use the property of Spherical designs. So Benkoff already showed if the generator forms the Spherical designs, we have this type properties for any vector alpha. If we sum those X belongs to Y, where Y is defined here, D is we write D as the union of Y and the negative of Y, where Y and minus Y has no points. This values the inner product alpha and X of square is a scalar multiple of the norm of vector alpha. And also we have this equation, the inner product to the fourth is scalar multiple of this value. This is true from the condition of spherical 5 designs. So if we rewrite these the equations using this new symbol nk alpha, this means the number of x belongs to y such that the inner product alpha and x is equal to plus k or minus k. Then the left-hand side of these two equations can be written as like this, k squared times nk alpha, or k to the 4 times nk alpha, because in this case, alpha must be in the dual lattice of L star. If alpha is taken from the dual lattice, then inner product, the vectors of the dual lattice in the original lattice must be integers. So this alpha inner product alpha x must be integer. So we can rewrite like this. Okay, so now we have these two equations. Just we consider the difference, these two equations. So we have a following equations, the summation of k to the 4 minus k squared times some values is equal to this complicated formula. So the point is this value and this value is of course positive, and we don't know this case, but the left-hand side is always positive. So this means right-hand side of this part is also non-negative. So we have from this equation, if alpha is taken from the dual lattice, and we assume this alpha has the following conditions, the inner product, the norm of alpha is equal to 2n plus 1 over 3. The right-hand side is equal to 0. So this means if k is larger than or equal to 2, for that k to the 4 minus k squared is positive. So this means nk alpha must be 0. So this means if there exists such vector alpha, then the inner product alpha and x must be 0 plus minus 1 for any x belonging to the set y. And Bannai Munemasa and Banks or Neve calls that case of minimal type, or already consider this case. So here is a definition of the minimal type. The lattice L generated by tight spherical 5 design is said to be of minimal type if there exists some vector alpha in dual lattice of L such that the norm is equal to 2n plus 1 over 3. So this is our conditions to guarantee solve the conjecture by Shu and Yu. Okay, so from this slide, we assume there exists such vector alpha, and we can calculate the n0 alpha or n1 alpha explicitly, because nk alpha satisfies these two equations. The sum of n0 alpha and n1 alpha is equal to the size of y, and these equations. So we can determine the n0 alpha and n1 alpha. And now we consider the set Z defined by this set Z consists of vector x such that the inner product alpha and x is equal to 0. And so this is inside of the statistical designs, but if we consider the vectors on the hyperplane defined by this equation, and also this we projected this to the one less dimension unit spheres. So this set Z forms an antipodal 3D set. This is a trivial case, but and also this size of D determined from this value N0 alpha. And now we have antipodal 3D set in one less dimension unit spheres with desired the vertices, number of vertices, and also this has the satisfies spherical design conditions, but we need one more lemma. I will explain this lemma in the next slides. So anyway, so this Z is our target, and this is for 3D sunsets with 3 designs. So we have a corresponding real title frames with these parameters, one less dimension case. Okay, so now I'll make sure the spherical designs conditions. Also, this was obtained by our joint work. So if we are given a spherical T design in S to the D-1, and we consider some vector alpha such that plus minus alpha not belonging to the original set X, and assume this set, the inner product of between alpha and X consists of some S value, say beta 1 to the beta S. And if we consider the subset Xi of the spherical T designs X, this set forms X such that inner product is equal to beta Y from alpha. And also we project to the one less dimension unit sphere. And if the spherical T designs T is larger or equal to S minus 1, then each set Xi forms a T minus S plus 1 designs on one less dimension unit sphere. So using this lemma, this set Z, this is a subset of the original spherical 5 design, but projected on the one less dimension unit sphere, forms still a spherical 3 designs from this lemma. I would like to mention that same is that this lemma is just a slightly generalized to the original result by the result both cited spherical designs in the spherical designs course. They claim exactly same lemma for the case alpha belonging to X. Okay, so the answer for the Sho Suda use conjecture is if tight spherical 5 design is so-called minimal type, we can find some another equiangular title frame from that. And I'd like to mention some more results about equiangular title frame. So this result will be in forthcoming our paper, but we can say more. The tight spherical 5 designs of minimal type is equivalent to some so-called coherent configuration. We can show this result using some the theory of spherical designs, and I think coherent configuration is very interesting object now. And this is the generalization of association schemes. And if we have a nice combinatorial object, we often obtain the association schemes. But if we consider the nice union of nice objects of, then I hope they form a coherent configuration. And this is the very algebraic object. And this comes from permutation groups, but I often consider the coherent configuration of a union of spherical design. So if you're interested in the result of a coherent configuration and Spherical designs, please look at this paper, Coherent Configuration and Triple Regular Association Schemes, appeared in JCTA almost 10 years ago. And also, this has a very nice property for me that it's a so-called Q polynomial. And this result will appear the LAA very soon. Okay, I talked too much, but this concludes of my talk. Thank you for your attention.
All right. Thank you so much. I'm going to encourage everybody to hit that reaction button. And thanks, Sho, for a great talk. And Dustin,